So far in our course, we have looked at conservation statements of mass and momentum, and surely these form the basis of forming conservation equations in fluid mechanics. Another conservation equation of great importance is that of conservation of energy. So, conservation of energy begins with the statement of the total energy of a fluid particle. The total energy of a fluid particle is comprised of the internal energy and its mechanical energy. So essentially, we have the rate of change of the total energy of a system so this defines the total energy, and E is the internal energy per unit mass. And half U square can be identified as the kinetic energy per unit mass. So now this rate of change of energy of the system will be equal to all the different work done on the control volume, or rather work done by the control volume, and heat transfers by the control volume. So now the work done by gravity, so it will be integral rho g dot u dv. This is the work done by gravity, essentially force times the velocity, rather the rate of work done. So this is the rate of work done by gravity. The second term will be, if we have a surface force, it will be the traction vector dot the velocity dv, plus, or rather, the loss of heat, or rather the input of heat. So if we have a control volume, if heat enters into the system, right, the energy of the system increases. So if heat is entering into a system, so if the heat flux, that is the heat per unit area, is Q, then the heat entering into the system will be integral Q dot N dA with a negative sign to indicate that this is the influx of heat. So this will include another term minus integral Q dot N dA over the entire surface. So this defines the statement of the conservation of energy. Now we're not going to go deep into simplifying this particular statement, but I'm just going to give a short overview, and perhaps in the later lectures we're going to look at the ramifications of this particular equation. But for now, it is sufficient for you to know that the rate of change of total energy of a system in an inertial frame is given by the total work done on the system. So this is work done on the system plus the heat transfers to the system. Alright, so these are sort of the works done on the system. So work done on the system will give rise to an increase in energy, while heat influx into a system will give rise to an increase in energy of the system. Let us now analyze various conservation equations in non-inertial frames. So an inertial frame is something which is either stationary or something which moves with a constant velocity. So we know from classical mechanics that these are called as inertial frames. But in many cases, it is not entirely convenient to consider a frame of reference which is fixed. In such references, we would often deal with frames which are translating or accelerating or rotating with respect to a fixed frame. So let us consider a fixed frame in space. Let us call it 1, 2, 3. So essentially it's E1, E2, E3. This is the origin. Let us say we have another frame like this. Let me call this 1 prime, 2 prime, and 3 prime. This is O prime. So essentially we have a frame which is translating and possibly rotating. So let this be the rotation vector in the non-inertial frame, and let this be the position vector of the frame of reference with respect to the inertial frame. So for any point in the non-inertial frame, if we write the vector as x prime, we can write x prime in terms of x. So this is capital X and this is small x. So any vector in the inertial frame, the stationary frame, can be written as a combination of xt plus x prime t. And this implies that the velocity as seen in the inertial frame will be the rate of change of the location in the inertial frame, and this is tantamount to writing d capital X dt plus d small x prime dt, and therefore the u is equal to, now dx dt is like the velocity with which the non-inertial frame is moving. So this will be, say, capital U plus, now this particular term is ddt of, say, x1 prime e1 vector plus e1 prime vector plus x2 prime e2 prime vector plus x3 prime e3 prime vector, where x1 prime, x2 prime and x3 prime are the components of x1, x2, x3 in the non-inertial frame. Okay, they are simply projections in the non-inertial frame. Therefore, we can write this as, so this chain rule will yield dx1 prime dt e1 prime plus x1 prime de1 prime dt plus dx2 prime dt e2 prime plus x2 prime de2 prime dt plus dx3 prime dt e3 prime plus x3 prime de3 prime dt. Now you may wonder, why have I taken the derivatives of e1 prime, e2 prime and e3 prime? So basically these particular terms are the derivatives of the unit vectors. So why have they come? It's because the coordinate frame is rotating. Even if I consider the coordinate frame like this, 1 prime, 2 prime, 3 prime, at a next time instant it is both translating and rotating in space. So at a next time it could be something like this. So 1 double prime, 2 double prime, 3 double prime. So the fact is the unit vector itself is rotating, and as you can probably guess, the rate of change of the unit vector has to do something with the omega. Well, let us not jump ship and let us see what happens. So u prime will thus be capital U t plus, so now dx1 prime, dx2 prime and dx3 prime, they are essentially the velocities as seen in the non-inertial frame. So it will be u1 prime, e1 prime plus u2 prime, e2 prime plus u3 prime, e3 prime, okay, plus the other terms, but we can combine these terms and write it as a vector velocity as seen from the non-inertial frame. So this will be u prime plus the derivative terms. Now, so let us try to analyze what the derivative terms will be. So let us consider that at a given instant, this is E1 prime. This is the axis of rotation. This is E1 prime, and at a next time instant, mm, in fact, in order to draw it clearly, let me, it's just for visualization convenience. Let this be E1 prime, and because of this rotation omega, this E1 prime will go somewhere over here. It is sort of rotating like this. Okay, so this is E1 prime at time t. This is E1 prime at time t plus delta t. So now what is d E1 prime? This is E1 prime at t plus delta t minus E1 prime at t. Essentially, this is, if you use the Taylor series expansion, this becomes d E1 prime dt times delta t. So d E1 prime from geometry is going to be E1 prime plus d E1 prime will give us, so it's just a triangle rule. Okay, E1 prime, this pink vector is equal to this orange vector plus the green vector. There is nothing but this particular statement. Okay, if I arrange this, E1 prime at t plus delta t, which is the pink vector, equal to dE prime, which is this vector, plus E1 prime, this vector. Okay, it's just a vector summation. Now we can also write down this dE1 prime in plane as something like this. So let me just, so this angle swept because of rotation is also this vector dE prime. So dE1 prime, or rather the magnitude of it, is going to be this r theta. Okay, so what is the radius going to be? So if this angle is alpha, so the radius will be sine alpha, because the magnitude of E1 is 1. So this particular radius is going to be sine alpha times 1, but it's the same thing as sine alpha, times the angle swept. And in time delta t, the angle swept will be equal to the velocity, angular velocity, times delta t. Therefore, d E1 prime dt times delta t is nothing but sine alpha times omega times delta t. So delta t cancels out. So d E1 prime dt is nothing but omega sine alpha. And if you pay attention, this d E1 prime is going to be orthogonal to both the vectors omega and E1. And so this condition and this particular algebraic condition is satisfied when this is equal to omega cross E1. Okay, so dE1 prime dt in a vector form is equal to omega cross E1 prime. So this is a very important thing to know. And when we substitute this particular relationship over here, so what do we have? We have x1 prime de1 prime dt. So essentially it's something like x1 prime omega cross e1 prime plus x2 prime omega cross e2 plus x3 prime omega cross e3. This is nothing but omega cross x1 vector. Okay, so if I combine this and this, it is nothing but omega cross x1 vector. So if I take these two terms and if I combine all these terms, this expression will be equal to omega cross x1 prime e1 prime plus x2 prime e2 prime plus x3 prime e3 prime. Okay, this is the one and the same thing. And x1 prime e1 prime plus x2 prime e2 prime plus x3 prime e3 prime is nothing but x prime vector. It is nothing but x prime vector in component form is this. Therefore, this entire term may be simplified simply to omega cross x prime. Alright, so let me just copy this over here. So the velocity as seen in the inertial frame is related to the velocity of the frame of to the moving frame plus the velocity in the moving frame, okay, plus omega cross r, I mean omega cross x prime. So this result I'm sure you might have done in classical mechanics, and this forms a part of the Chesel's theorem. So now that we know that the velocity is equal to the velocity of the frame of reference plus the velocity inside the frame of reference plus omega, the rotation rate of the frame of reference, cross the location with respect to the frame of reference. Just for convenience, I'm gonna draw the fixed frame, the rotating frame, and the object. So the frame is sort of having some angular velocity. This is capital X vector. This is x prime. So x prime is relative to the frame. Now, if I want to find out the acceleration from this, what will be the expression? It will be ddt of this entire term. So ddt of capital U t plus ddt of u prime plus ddt of omega cross x prime. So this is going to be acceleration of the control volume, which is in the non-inertial frame, plus what is this term going to be? It is going to be the acceleration as seen in the frame of reference, in the moving frame of reference, plus omega cross u, and this comes out from the Chesel's theorem. Alright, ddt of a vector is comprised of the direct differentiation of the vector plus the rate of change of the basis vectors, and this accounts for the rate of change of the basis vectors, and the basis vectors are strongly related to the rotation rate of the frame. We already know this from the previous derivation. Alright, plus from this we will get two terms, rather three terms. The first is derivation of only this term, so this will be alpha cross x prime. Then we will have derivation of this term, and that will give us omega cross u prime and the rate of change of the basis vectors plus omega cross x prime. Okay, just use Chasel's theorem to derive the fact that this particular term is equivalent to this. So the acceleration as seen in the inertial frame is equal to the acceleration of the moving control volume plus acceleration of the object seen in the moving control volume plus, so this becomes twice omega cross u prime plus alpha cross x prime plus omega cross x prime. This particular term is the acceleration of the moving frame. This is the acceleration as seen in the moving frame. This is the Coriolis acceleration. This is the angular acceleration term. This is the centripetal acceleration. Alright. So this is a very important result, and possibly you have done this in some form or the other in your classical mechanics courses. So now let us write down the statement of conservation of momentum. Actually, any kind of derivative, gradient or derivative, it does not change because of the moving frame. Because suppose we just consider a one-dimensional problem, that is x equal to capital X plus x prime. So del any variable del x will be del any variable del x prime times del x prime del x, and del x prime del x is 1. So it is the same as del phi del x prime. So the gradient or derivative does not change, but the time derivatives keep changing, and the time derivatives change because of the fact that the control volume is moving, is translating, and the fact that the control volume is rotating. So if you account for these two facts, you obtain such an expression for the acceleration. So now let us proceed to write down the statement of the conservation of mass. So conservation of mass, actually we don't need to really bother about because it is unchanged. Actually conservation of mass is independent of the frame of reference, and that should have been quite obvious. Now let us look at the conservation of momentum. So rho du dt, right? The integral of rho du dt, actually ddt of integral rho u dv is equal to summation of all the forces acting on the control volume. So this statement is true in an inertial frame. You all know this, that this Newton's law is true in an inertial frame. So the left hand side becomes integral del t of rho u dv plus integral rho u dot n dv, and this is going to be summation of all the forces acting on the control volume. This should be dA. So we've already made use of the divergence theorem and all, and we have shown that the left hand side is actually tantamount to integral rho du dt dv. This is equal to summation of all the forces acting on the control volume, and we have derived this in a few lectures ago, and this is obtained by making use of conservation of mass also. So if you don't recall this, you can actually derive it. You can make use of the divergence theorem and convert this normal flux into a divergence term and make use of the conservation of mass to obtain this. If not, you can always look up the earlier lecture. So now we will make use of this particular result. Okay. So now before that, what are the expressions of the forces? So it can be due to the body force rho g dv. It can be due to pressure gradient minus grad p dv. It can be due to traction vectors f dA. Alright, no problem. So the left hand side we can write down as rho. Now du dt is the same as du prime dt plus acceleration of the control volume plus twice omega cross location of the control, not location, the velocity in the control volume plus alpha cross x prime of the control volume plus omega cross x prime in the control volume dv. This will be equal to integral rho g dv minus integral grad p dv plus integral fraction vector dA. So then what do we have? We can isolate this particular term. So it will be integral rho du prime dt. So this is vector obviously. dv is equal to minus integral grad p dv plus integral rho. Now I will combine this g. So this again, this is going to be g vector. I've written it as g, but it's actually going to be a g vector. So plus rho common, g vector minus du dt, that is the acceleration of the control volume. Okay, in fact, again, let us write it as ACV only, minus twice omega cross u minus alpha cross x prime minus omega cross x prime dv plus integral f dA. So all these integrals are over either control volumes or control surfaces, or the surface of the control volume. And this is a statement of the conservation of mass for a control volume which moves with an acceleration given as this and which rotates with a velocity given as this. And if additional information is given about the angular acceleration, it is accommodated over here. So all these in the non-inertial frame are understood to be pseudo forces. This particular pseudo force happens when a control volume is accelerating. Inside the control volume, you will feel a force in the negative direction. And we all know this: in a moving lift or accelerating car or an accelerating bus or a deaccelerating bus. You know several examples from your JE days. What is this? This is the Coriolis acceleration. So what exactly is the Coriolis acceleration? So if I want to explain the Coriolis force, let us see. Let us take a simple example. Let us consider a disk like this which is rotating. So the rotation vector is towards us, and let us say I strike this carom piece along this direction. Alright. So if I am standing in the lab frame, then I will see that the carom piece, so if it's a completely frictionless disk, then the carom piece will only move in this direction. But now if I stand at the center line, then what will I see? So now my reference frame is rotating like this. So the carom piece will appear to actually move backward. I mean, it will appear to move in this direction. So if I am looking at this moment like this, at the next moment like this, so the carom piece in our frame of reference, which is lab frame, it is moving like this. But when I am looking like this, it appears that the carom piece is moving in this trajectory. So why is it appearing to move in that trajectory? In the non-inertial frame, the velocity vector is this and the omega vector is out of the plane. So what is omega cross u? Omega cross u will be in this direction. So minus omega cross u is in this direction. So it will it will appear that there is a force acting on the disk which causes the trajectory to become something like this. Let me draw a larger disk. So when it is hit, it the force is in this direction. This force is minus twice omega cross u prime rather. So this is omega out of the plane, this is u prime. So this is the force. So when the particle starts to move, it will appear that it will take this trajectory. So after a time delta t, the displacement, not the force, this is the acceleration. So this is not the force, this is going to be the acceleration. So a Coriolis. So after a time delta t, the distance moved. So s will be half acceleration times t squared. So twice omega cross u, the magnitude of that, delta t square. So 2 cancels out. So it will be omega times u times delta t square. So this is the displacement, this particular displacement. Alright. In in that particular amount of time, the particle has traveled a distance L is equal to u prime delta t. Alright. So the particle should have moved a distance of L while it faces a displacement in the perpendicular direction of this particular. So the angle. So if I call this angle as alpha, let's not mix up alpha. Let's call it theta. So tan theta will be equal to S upon L delta t cancels out, this cancels out. So this comes out to be omega delta t. And for small times, tan theta will be theta. So delta theta upon delta t will be equal to omega. So it appears to deflect by this angle. So it appears to deflect by this particular angle. But from this particular reference frame, this delta theta is actually the, so if I consider a fixed point somewhere on the disk, this disk would have moved this particular angle in time delta t because the disk is rotating with a velocity omega. So the deflection of the disk, rather this particular straight line that we see that I've drawn over here would actually rotate for an observer standing inside the non-inertial frame. So the trajectory that the observer in the non-inertial frame would see is in this direction. The direction is continuously changing because it's continuously rotating, but it would eventually have a deflection which will cause it to always maintain that straight line. So what this observer sees is that a frictionless disk will keep on moving like this, and what an observer inside the frame will see that that deflection is exactly balancing out the angle of rotation. So then both the reference frames will have seen the actually the same motion, but in one of the frame there is no force, but in other frame, in order to account for the deflection, there is a pseudo force, and that pseudo force is the Coriolis acceleration. And it is worth thinking a lot about this in order to clarify any doubts that you may have. The other terms are very easy to understand. This is due to angular acceleration and this is due to centripetal acceleration. So if you have an object spinning, so if this is the omega, so in the frame of reference which is rotating, if you are standing inside the frame of rotating reference, there will be a pseudo force which is trying to throw everything outside. So let us see the sign. So it is minus omega cross x. So this is x prime. So omega cross x will be in this direction, and omega cross this is in this direction. So omega cross x is in actually this direction. So this is the direction of omega cross x, but the minus of it is in this direction. So it appears that there is an outward force which is trying to throw away the object. But for an observer in this particular inertial frame, that if the object is trying to maintain its path, there is a centripetal acceleration towards the center. So there should be no ambiguity in what is going on. All these are things which you might have studied in classical physics, and this is just a quick recap of all those things. So essentially, the Gurney equation is this. In fact, let me copy it for clarity. Okay. Let us consider a simple problem to elucidate this particular concept. Let us consider that there is a tank, pressurized tank, and there is a small exhaust to the tank through which a jet always comes out at a velocity capital V. The initial mass of the tank is m naught, and there are wheels. It's moving on a frictionless surface, and this is not at all an imaginary example. You can imagine this to be some sort of a rocket or something, no problem. So the question is, form a differential equation for the evolution of the velocity of this entire assembly. Okay, so regardless of the velocity of this entire assembly, the exit velocity relative to the tank is always going to be capital V. Okay, so uh, let us see how we can make use of whatever concept we have learned. So first of all, the conservation of mass, right? So we have ddt of integral rho dv plus integral rho u dot n dA is equal to 0. Conservation of mass, it remains unchanged. Okay. So then what do we have? This is going to be dm dt, and what is this term going to be? So it's going to be whatever is exiting. So u dot n is going to be positive because the n vector to this exhaust area is also in this direction. So it will be m dot e, where m dot e is equal to the velocity, density times velocity times the area of the exhaust. Alright, so this is m dot e equal to 0. So essentially dm dt is equal to minus rate of exhaust. Now the more involved part, let me copy this equation downstairs. Let me just copy this schematic also. Alright, so what do we have? This entire, we fix our reference frame moving with this particular entity. So this is x prime y prime, and the inertial reference frame is this. So this is the inertial reference frame. This is the moving reference frame. The reference frame is actually moving with a velocity of capital U. All right. So what is this gonna be? So because there is no sort of rate of change of momentum inside the moving reference frame, this entire term is gonna go to 0. Actually, this is the total derivative. Let me write down the left hand side completely. So this is going to be, in fact, this is going to be ddt of integral rho u dv, or rather rho u prime, plus integral of rho u prime u prime dot n dA, and the right hand side remains constant. So for the left hand side terms, this becomes, so this is not changing for the control volume. Whatever the content in the moving frame is, in the moving frame actually nothing, this entire mass has no momentum. Mass of liquid in the moving frame has no momentum, but it is having a flux in momentum. So this particular term becomes 0. The flux in momentum is actually in the negative direction. So u prime in the moving frame is simply v. So this will be minus rho v, and u dot n cap is going to be v times a, and this is going to be into RHS. So this becomes minus m dot exit times v is equal to the RHS. Now what about the RHS? So pressure difference, there is no force as such because of the pressure difference. Everything is vented to the atmosphere. So this is going to be 0. No effect of gravity. Now this term will exist. So we have minus rho times ACV times dV. So essentially rho ACV dV, this is going to exist. There is no rotation, there is no angular acceleration, no rotation, no traction vector. So what is this term going to be? It's going to be minus du dt, this is the acceleration of the control volume, times integral rho dv is the mass of the control volume. Okay. So what do we have? Finally we have, okay, let us write it down as rho v square a. So we have minus rho v square a is equal to minus m du dt, or effectively du dt is equal to rho v square a upon m, where m is actually found out by integrating this. So if I integrate this, because m dot a is going to be a constant, so m is going to be m naught minus m dot e times time. So this is obtained simply by integrating this one. So over here this becomes rho v square a upon m naught minus m dot e times time. Now du dt is rho v square a upon m naught 1 minus m dot e by m naught times time. And you can easily integrate this. There will be a logarithm coming into the picture, but I'm not gonna go ahead and do that. I'll let you enjoy doing that integration. It's a very simple integration, nothing challenging about it. But the important thing is the concept. The concept is in the moving frame, V is going to be constant. This momentum content on the left hand side is not going to change, right? So all that is going to change is the right are the terms on the right hand side is the fact that the control volume itself is accelerating. That's going to create changes in the equation. The acceleration is going to give rise to this kind of a pseudo force, which helps us in finding out the velocity of the moving tank. It's a very simple problem. Alright, let us now quickly do a problem on the conservation of, or rather let us look at some basic building blocks of the conservation of momentum. So we've already seen the conservation of uh, momentum as this. So here B is the velocity of the control volume, okay, in an inertial frame. So B is constant, of course. We've already done the entire non-inertial part in the previous derivations, but here B is moving with a constant velocity. That is, we're still in an inertial frame. Anything which moves with a constant velocity is still an inertial frame. It's not accelerating. The moment you have accelerations, you will end up with pseudo forces appearing over here. But anyway, so this is the statement of the conservation of momentum, but we want to expand this to the statement of the conservation of angular momentum. So what do we have? We have ddt of integral rho r cross u dv plus integral rho r cross u minus b dot n dA, and this will be equal to summation of all the moments acting on the control volume. Alright. Moreover, if we select a control volume which is rotating together with the frame of reference, then what do we have? We will have ddt of integral rho r cross u prime dv plus integral rho r cross u prime minus b dot n dA, and this will be summation of all the moments minus the moments of the pseudo forces. So rho r cross all the different terms dv. Now what are all the different terms? It will contain acceleration of the control volume, okay. It will contain twice omega cross u prime Coriolis acceleration plus alpha cross x prime plus omega cross x prime. So it will contain all these as pseudo forces, and it is most easily understood by means of an example. Let us consider all the different terms in a very simple illustrative example. We're not going to solve the problem fully, but the problem is going to show you how to approach all the different terms appearing above. So let us consider a water sprinkler. It's mostly a straight line with just some exits like this. Okay, so this is the pivot point. The pivot point is given to be frictionless, and the velocity at the exits is v exit. And if the velocity at the exits is v exit, the velocity throughout the channel will also be v exit. Now we fix ourselves in the coordinate frame of the sprinkler. So this is rotating, this coordinate frame is rotating, and because of that we'll end up with all these kinds of terms. So the first thing is this particular moment will be 0 in the frame of reference rotating with the sprinkler, because it's a steady state problem inside the frame of reference is rotating. So this particular term vanishes. So the second term is essentially integral rho r cross u u dot n dA. So u dot n, because b, that is the velocity of the frame of reference in the rotating frame, is also 0. Okay, this is actually the velocity of the frame of reference in a given velocity of the control volume in a given frame of reference. So b is going to be 0, right? So this is the term. So and this can be simplified as, so what is r cross u? So r cross u, so this is going to be integral. So now this is the, okay, before going to the evaluation of the integral, you have to remember that these are the velocities in the reference frame, moving reference frame, evaluated at the surface. Alright, so this is rho at the surface. This r cross u is going to be ri cross vej, and u dot n cap is going to be veae. This integral can go away because we have integrated it, and ve is constant over the entire exit cross section area. So this becomes rho ve square ae times r, and I cross j is k. Now similarly at the other side also we're going to have another term like this. So on the other area, this plus rho, so it's going to be minus r in the I direction plus cross ve in the minus j direction times veae, because veae is the flux coming out through this, and ve times ae has the same direction, no problem. So ve dot ae is going to be positive. So it's going to be, so this minus minus becomes positive, and this is going to be the same term. So essentially you get twice of it. So this is essentially the flux of the angular momentum coming out. Now let us turn our attention towards the right hand side. So we have these terms, integral r cross. So first of all, the ACV term will become 0 because the control volume does not have any linear acceleration. All it has is rotationality and rotational acceleration. So this ACB will vanish. Then you have uh, minus rho. So rho we can take out because rho is going to be a constant. So r cross twice omega cross u prime. We're going to have minus rho integral r cross alpha cross x prime, so dv, and lastly minus rho r omega cross x prime dv. Now remember that all these integrations are over the control volumes, not over surfaces. So at a given location r, what do we have? So let us evaluate the first term. So it's gonna be minus rho integral r is going to be ri cross twice omega in the k direction cross ve in the I direction, because u prime at a location r is going to be ve, but now in the I direction, unlike this part, and dv, so the volume is going to be the area of cross section times dr. So this becomes minus rho, so this 2 omega, so this omega is not going to be a vector because I've accounted for the k vector over here. So it's going to be minus rho, 2 omega comes out, VE comes out, AC comes out. Okay, so K cross I is going to be J, I cross J is going to be K, so there's a K vector over here, and it's going to be integral R dr, and R is going to vary from 0 to capital R. But actually you can easily verify that whatever this is, right, the same term is going to appear on this side also. So there's going to be another 2 factor over here. And it's quite easy to see because this R will have a negative sign. This will be minus Ri. Omega not going to change, but V is also going to change its sign because V is also at a distance minus R. It's going to be in the minus VE I direction. So two negatives will become positive. So it boils down to the same integral. Okay. So what is this going to be? Minus 4 rho omega VE AC. This is going to be R square upon 2. So it's going to be R square upon 2. So this is how you would evaluate the first term. Now what about this particular term? Let me make a new page. So it's minus rho integral R cross alpha cross x prime dv. So minus rho. So now this is integral of R vector in the I direction cross d omega dt in the k direction cross R vector in the I direction dv. But dv is nothing but R, so rather dr times the area of cross section. This is minus rho area of cross section d omega dt. So it becomes, so k cross I is going to be equal to j. So I cross j is going to be k. So there's a k vector over here. It's going to be integral r square dr going from 0 to r, and this is going to be minus rho ac d omega dt k vector r cubed upon 3. So once again, we're gonna have a same contribution from the left end as well, because on the left end we will have minus ri. D omega dt is not gonna change because rotationality is still in the k direction, and the r vector will be minus ri. So double negative will again become positive. I hope it's clear. So there will be into 2 also. So this is gonna be minus 2 by 3 rho ac r cubed d omega dt in the k direction. So far we have this in the k direction. The left hand side is also in the k direction. This is also in the k direction. So far so good. We look to have obtained all the expression. So what about this term? So omega cross x. We know that the centripetal acceleration throughout the volume is going to be in the I direction. So and r is also gonna, so this entire term is in the I direction, but r is also in the I direction. So the cross product will vanish. So there will be no angular momentum content because of the centripetal acceleration. This term will have a zero contribution. Okay, so I'm not going to proceed further with this problem. You can collect all the terms, form a differential equation for omega, what the rate of change of angular velocity. So you can easily find out what the rate of change of angular momentum is, or the angular velocity is for the control volume. But the important points, I'm going to recap the important points once again. The flux on the left hand side requires you to evaluate. So it requires you to evaluate the velocities at the exit. These are r cross u velocities at the exit. These are not volume integrals, but these are area area integrals. Similarly, these particular terms, that is the contribution of the the pseudo forces, they are evaluated not at the areas but throughout the volume. So the velocity appearing in these expressions are those inside the volume, while in the fluxes are evaluated at the surface. The velocity at the surface was oriented along the j direction, but the velocities in the volume are mostly directed in the I direction. That is a very important point of distinction, and you should not miss it. Anyway, for an undergraduate course, this can be considered as advanced materials, but still it is worth knowing all these facts.